Hi guys, welcome to today's recording. Today I'm going to go through the level 3 chemistry spectroscopy internal standard. So I did make a couple of videos last year, and so if you are wanting like the basic instructions, I believe one of them is going through all of the three kind of spectra that we are going to go through in the standard, like in fairly great detail. So what particular features you're looking for on each particular spectrum. So I would strongly, so if you're very confused, I would strongly recommend you to go through the playlist and find that particular video that goes through all of the very details of how to, you know, just find the basic structures, like basic features to get you the achieved. Now and another video that I made last year also just went through some questions. Now in those videos, I just want to make it really clear now, because we had some feedback from external moderation. We, like us as a school, we weren't very focused on the molecular on the fragmentation on the mass spectrum, but you do need to do that now for excellence. I think for merit as well, so but definitely for excellence. So I will go through that bit while I go through some questions. So this is more of a because my school has their internal next week, so I'm just going to go through some practice questions for mainly my students, but obviously I'm doing this for the greater community. So if you know someone that's struggling in spectroscopy, feel free to send this video to them. So let's just get, because I just want to make it really clear that the fragmentation wasn't included in those two other videos, but based on the feedback that we got from NCEA, that it is absolute required from well, should have been required from day one, but we just didn't really do it. But you know, it's never too late to edit them. So the table that you see on the left hand side, on the very top left, that's a result sheet that we provide to our students. Now I've obviously done a bit of tuition, and I've seen what some other schools have done, because the internal standards is really up to different schools. So the result sheet may look a little bit different, especially, so this is the I can't see my mouse, but this bit here, this is the IR table. I do know that some schools go into the fingerprint region, which is the 1500 centimeter 1500 wave number or lower, which I personally don't really like, because you know, you don't look at someone's fingerprint under, you know, you when you meet someone, you don't look at the fingerprint and try to figure out who they are. You know, you look at their face, you look at you hear their voice, you know, you don't look at the fingerprint. So I just personally don't think it's a really good idea to look into the fingerprint region. So as our school, we don't do it, but if your school does require you to talk about the fingerprint region, so obviously go with your teacher said. So mine just this is mainly targeted at my students, but the general content doesn't change, but you know, just because different schools assess them differently, so just be mindful. Okay, so my tutorials, especially the examinations one, definitely work for all the schools, but for the internals, that's really sometimes up to the school's discretion to decide how they want to run it. Okay, so so check out those two videos if you need the very basics. I'm just gonna go straight into some questions. So you got the tables on the left hand side. I may come back to and refer to them every now and then, but let's just get started. Okay, so the first one that we're looking at, so we got three spectrum representing only one of the molecules below, and then so this is obviously not one of those properly printed, like especially this the IR that you're looking over here. This is hand drawn, so it's more of a just to teach you the content pretty much. And if you get a question like this, you know, the selection questions, if you're choosing one that fits all of them, I personally highly recommend you, like I say this to my students, before you even write any answer, like write anything down, just go through all of the options and go through the you know, look at the carbon environments, blah blah blah, and that will straight away eliminate a lot of the wrong choices. And then once you figure out what the final answer is, and then you can come back and talk about it. Okay, so, and again, in this video, I'm not, because I already provided the notes for my students in class, and I'm sure you're not here to read, you know, 2 pages of mod answers because I'm sure your teacher would have provided something like that. But so I'm just going to go through the thinking behind the the solving of this particular problem. Okay, so without further ado, let's get started. So first thing first, I like to do the carbon environment. So this is 1, 2, 3, 4, 5. So carbon molecule 1 has 5 environments. This is 1, 2, 3, 4, 5. This is 1, 2, 3, 3, 4, 4. This is 1, 1, 2, 3, 4. This is 1, 1, 2, 3, 4, 4. Again, if you want the more thorough explanation of how I determine those, have a look at my other clip, okay? Because I don't want this to be too long. So straight away, we know this has 5 carbon environments, this has 5 carbon environments, this has 4, this has 4, this has 4, and then we come back to the NMR, and please don't get confused which one's the NMR. NMR has a unit of parts per million. So we've got 1, 2, 3, 4 peaks. So it's showing us 4 peaks. So that means A and B is wrong because they're showing 5 carbon environments. So they should be giving 5. So it's either C, D, or E. Okay. And now we look at the molar mass. I do want to go through at the end of the video. I do want to go through the mass spectrometry a little bit in bit more detail with the isotopes. So because if you get that one wrong, then you're gonna get the whole question wrong. So I'll do that at the end. But if you look at this 101, so this is the molecular ion, which is the that tells us the molar mass, which is 101 grams per mole, and that's an odd number. Odd number means we have a nitrogen, and then let's go have a look. There's a nitrogen here, there's a nitrogen here, there's a nitrogen here, so they all have nitrogen, so that doesn't really help us. And then if you also look at the mass spectrum, there's no chlorine, there's no Br, because remember, for achieved, you do need to give us a couple of features about each, like from what you can determine from the spectrum. And I always emphasize that what you could see and what you don't see are equally important. Okay, so there's no Cl isotope, there's no Br isotope peak, so that means it's not in the thing. And then if we come back to the IR, come back to the IR spectrum, this is clearly a C-double-bond-O. Now, if you see a peak right on 3000, this is always CH. Okay, because I've seen people like, say for example, if I just do one really quick here, like, so if I see people doing 3000 and then they're like, oh, so is that an H or OH or CH? If it's right on 3000 or just, approximately in that, plus minus 50 region, that's always going to be CH, and all organic molecules have CHs. So that's really, really not the most important thing that we want from the spectrum. So we don't really care about that. Now this thing here, this is an NH. Now this is why I don't want, like, especially with this type of question, guys, I don't want you to look at the IR and start scratching your head and go, all right, is this IR or is this OH or NH? That looks quite broad. That's probably OH. But is that OH, is that NH? Don't waste your time on determining that. Look at the molecule first, okay? Look at the molecule, start eliminating using the carbon environment, look at the nitrogen rule, and then once you got to the final couple, then you can come back and say, all right, this has to be NH because there's no OHs elsewhere, okay? Because the general rule of thumb is that if you have a broad peak is OH, a sharp peak is NH, but I've seen sharp OHs, I've seen broad NHs, so it's more of it's kind of a gray area because it's not really consistent all the time. Okay, so we know this has C-double-bond-O, NH. All right, so this peak here, this is C-double-bond-O, and there's the 2 peaks here. This is clearly like a CH3, and these 2 here is probably, because we know we have a C-double-bond-O, it's potentially a carbon that's bonding to the C-double-bond-O, and one of them, because we know we have an NH, so one of these could be a C single bond end, and one could be the other way. So I don't know which one's which, so but one or the other. So that's our structure. Now if we come back to here, we can clearly see straight away, look at the nitrogen side, C and D are wrong because they don't have NH bonds. So D is a correct molecule. So there you go, we solved the question. Now how do we write about it? So you need to eliminate, like say for example in this case, I'm just gonna go A and B are wrong. So first of all, I'll talk about from the mass spectrum, this is what I can see. From the IR, this is what I can see. From the NMR, this is what I can see. All right, so therefore A and B are wrong because they have 5 carbon environments and the NMR is showing 4, eliminated. C and E are wrong because the IR shows there's an NH bonds, but C and E both don't have NH bonds, so they're wrong. So D is the correct answer. Now you can't just say, all right, through elimination D is the correct answer. If you do that, you probably just get achieved because you're not using all of the spectra to link back to the justification of how you determine that this is a correct molecule. So what you need to do here, you need to say, all right, so this has 4 carbon environment, which matches this one. It has a C double bond, which matches here, matches the IR, matches the NMR. There's a nitrogen here, which matches the odd number molar mass, and there's an NH bond here, which matches the IR. So you try, and then there's a CN single bond on the NMR, one of these peaks, and you need to use all 3 spectra, link them together, and sometimes you just use, like say if I can see the C double bond O on the IR, I can also see the C double bond O on the NMR, which is the confirmation that it actually exists. All right, so it's a bit over the top, but that's what NCEA wants, so we're just gonna do what they ask us to do. Okay, now one thing that I do want to talk about is fragmentation. Now fragmentation is something that we know this is the right molecule, and I just want to make your life a little bit easier if you've been struggling with fragmentation. Fragmentation is not something that you should spend too much time on. It's more of it's just a cutting exercise. All right, so if you watch my organics videos, you know that I talk about cut and paste a lot, heaps in that particular standard. And in this one, it's no difference. Because what is fragmentation? Fragmentation is pretty much just, this is my whole chain of molecule. Put that into the machine and that gets vaporized and then it gets ionized. So I just tell my guys it's literally like you're having a knife and just cutting that into smaller fragments, and these smaller fragments comes up on the machine. So most obvious fragments, that's almost like so in this case the easiest one to do, and you can go from left to right or right to left, it doesn't really matter, but the easiest way that you can do is to do this. Like say I can cut here, and so this is one fragment, which is my CH. Don't forget the plus sign because this is an ion, because they're all been ionized. And CH3 is equivalent to 15 grams per mole, and 15 grams per mole is this peak right there, 15. Now this is, and then if you add up the rest, this is going to be 101 minus 15, 101 because it weighs 101. 15, this is just going to be 86. Okay. Obviously this mass spectrum is a little bit simplified, so it doesn't really show the 86 fragment, but this is one that you can say this 15 is CH3. It's not really but then if you look at the molecule, this has CH3, this has CH3, this has CH3, all of them has CH3. Okay, so it's not really the best way to do it. What we can also do is that you can cut elsewhere. You can cut here. If you cut here, this is 15, this is 15, this is 13, so it's not on here, so probably don't want to cut it this way. What if we cut it this way? If we cut it this way, this is 15, this is 1, this is 14, so that's 30. So this 30 is going to be this one right here. Okay, and then so this particular NHCH3 is actually a really good fragment that you cannot find anywhere else in the other molecule. Like say if we look at the ABCE, like how the heck are you gonna get me 30? There's no way on earth that you're gonna get me a fragment that is 30 grams per mole. So if you cut here, let's say if you cut here, this is 29. If you cut here, this is 14, this is 16. Lies, you can actually get this one here, this is actually 30. So this one also works, but we know that one's wrong because it doesn't have the right number of carbon environment, so we know it's not that one. Okay, this doesn't have 30 and this doesn't have 30. So you have to link at least one correct fragment or one pair of fragments to the mass spectrum in order to get you excellence. So you have to use that as well, and it's really easy. Just draw the molecule and cut it and start cutting it, and you're trying to find, because you know this is the right answer, because we've done all the hard work before and we determined that this is the right answer. Just draw it on a piece of paper and just use a pencil or use a pen and just start slicing it, all right, and just go, all right, can I find this, can I find this? If you find this 15, if you find this 15, you're going to find 86. You're going to find the 86 somewhere here, and you can go, right, 15 is a CH3 plus, 86 is this, you know, and that will be good enough. Okay, so but that is absolute a necessity. I'm pretty sure that's required. All right, so that's the first one, pretty straightforward. But again, with the explanation of why D is a correct molecule, you can't just say through elimination is the right one. That's not going to get you anything. You've been warned. You do need to link back to all of the spectrum. You can't just say, oh, this is the right one because it has an N, it has a nitrogen, it has a fluorocarbon environment. You actually have to link them to each of the spectrum, and you also have to use combine all of the spectra together to give you the correct answer. Okay, so it's like, all right, this is a correct molecule because the molar mass is odd number, which tells me I have a nitrogen, which I do have, and then which is also confirmed on the IR because I have an NH bond. You know, if you have a nitrogen, you most likely have an NH bond, and then I have the C double bond over here, I have the C double bond over here, you know, showing up on two different spectra, which means it must be correct. Okay, so something like that. All right, let's try this one. So all of these questions that I'm doing are quite straightforward. Because like I bombarded my class with tons and tons of questions. I'm sure if you're doing this internal, your teachers would have done the same. Okay, so hopefully you haven't seen these. Just want to give these to you as a practice. Now, so this one's pretty easy, only 3. So this is 1, 2, 3. Obviously, do the carbon environment first. 1, 2, 3. This is 1, 2, 2. So this is showing a 3 carbon environment. So this one's wrong. That's only giving us 2. If you look at the IR, this is C double bond O, this is NH, this is C double bond O. If we have an NH, then this is most likely, this is 60, about 60. So it could be 2 things. It could be C single bond N, it could be C, CO, it could be one of those. Not sure which one it is, so we just question mark that. Now on the mass spectrum, we know the molecular ion is this one, guys. So remember, so I'm just going to draw that a little bit bigger. So this is what you see there. All right, this is 107. This is 109. So remember, if you, in this case, you can clearly see, like look at that pair, look at that pair. This is clearly a Cl3-1 isotope. So that means the one on the left hand side is the molecular ion, and then the one on the right is the one that we ignore because that is due to the presence of chlorine isotope, so we don't look at that. So the molecular ion is 107. And if you want to use a chlorine, like say, I know some people want to calculate the molar mass. If you want to use calculate the molar mass, don't use 35.5 because you're not going to get a 0.5 on your mass spectrum. Use 35, okay? Because this is how the 107 has been calculated, is by using chlorine 35. Don't use 35.5, okay? So we know the molar mass is 107. We know this is a 3-to-1 peak, so we have a chlorine, yay, bromine, nay. So, you know, that's all the information I got. So in this case, it's either this one or that one. So it's the first molecule or the second molecule, and if you actually take a closer look, it's actually really difficult to distinguish by just looking at them. I mean, if you look at them now, that one there, and then we can do the fragmentation. I can show you one of these fragmentation. So I'm just gonna cut it here, cut that there, which is the CONH2. So the fragment is CONH2 plus. This is a fragment. The other fragment is the CH2CH2Cl or CH3CHCl, you know, the other half. So if you actually add this up, this is going to be 14 plus 16, 12 plus 16 plus 14 plus 2, 30, 44. 44, boom, right there. This is a base peak right there. This one here is 44. This is a base peak, so this is showing us a fragment of CONH2 plus. This is a fragment here. But you can see that both of these molecules would have exactly the same fragments, because this one here, this big fragments will look exactly the same. Okay, so what you could do is you can try to look for the other fragments. You can start cutting it from this side, and this is why fragmentation doesn't work that well, because as you can see, as you can see on the spectrum here, it's actually really difficult to see, you know, do I have a fragment? Like if it's this tall, is that a fragment? If it's this tall, is that a fragment? So it's really, you know, difficult if you don't know what the correct answer is. So I wouldn't recommend you using the fragment to find out what the answer is. I would strongly recommend you to use the fragments to after you determine what the answer is and come back and justify it. Okay, so how do we know which one this is? This comes down to look at the carbon environments. All right, so if you look at these carbons, so this carbon here, I'm just going to label it, I'm just going to highlight that. So this carbon here is going to be this peak. Okay, now can you see, oh, this is not a this could be CN, this also could be CCl. In this case, this is a CCl. Now, can you guys see now this? So this carbon's out of the way. Now, this carbon here that I'm highlighting, this carbon here, this would be this one here. Sorry, it's a bit messy because this has a CCl environment, so that will be between 30 and 60. And now, can you see this carbon that I'm highlighting? Actually, I'm going to rub out all the other crap so you can see. This carbon that I'm highlighting right now, this is the carbon that's bonded to a C double bond O. So this carbon here, technically on the sheet, will be between 30 and 60. But then the problem is that if you look at this carbon is a CCl, which is also between 30 and 60. But then if you look at the spectrum, there's only one peak between 30 and 60. So that means this is wrong, because that would require, so if that was the correct answer, that means this particular peak will need to move up a little bit more. So that means this molecule, the first one on the left, is a correct one. Why is that? Because if we get rid of all the other drawings that we just did, I can label them together. So this carbon is that one, the CCl is 30 to 60, which is that one, and the CH3 is 20. Perfect. So this is a correct answer. Okay, so that's how you can determine it. Now, if this is when you can go back to the fragmentation, and then you actually, you know, because I tried to do this myself, and you might actually struggle a little bit with the fragments, because, like, say, how do I distinguish it? You know, the easiest to distinguish it is cut here and look for the 15, which is right here. You can't really see. There's actually no fragments here. Okay, so, and then the next place you can cut, like say if I draw them over here, you know, I don't recommend, because some people ask me like, so can I cut them like this? Can I cut them like that? Yes, you can, but that's gonna make everything very, very confusing. I tend to just tell people to cut here, look for the 15, and then cut here and look for the 44. Look for this side, and then look for this side, which we did find, which is a 44. So you can justify, you can just say the 44 is a COONH2 plus, and then the 107 minus 42, you know, whatever, 44, whatever the number is. So it's 107 minus 44, which is going to be 63, boom, this peak here. So we can say, all right, so what can we say? The justified, so the 44 MZ is a CONH2 plus isotope fragments, and then the 63 MZ is the CH3 CHCl fragments. Done. Okay, so you can explain that, and then again link back to the spectrum and, you know, talk about everything. Here's the last one. All right, so this again is a selection question. So first thing first, let's do the carbon environment. Just get into the habit. You know, when you do a selection question, just do something like this. I do have another type of question, which is, you know, figuring out the molecule from scratch, and that's on my other video, so you can have a look at that one, how to go about doing those. But my main focus, because our school is our type of question, so my emphasis is going to be this one. Okay, so 1, 2, 3, 4. This is 1, 2, 3, 4, 5. Oops, well, how did I write the 5 here? This is 1, 2, 3, 4, 5. This is 1, 2, 1, 2, 2, 3, 4. This is 1, 1, 2, 3, 4, 5. This is 1, 2, 2, 3. So this has 4 carbon environments, this has 5, this has 5, this has 4, this has 5, this has 3. And if we look at the mass spectra, the NMR right here, this is 1, 2, 3, 4, 5 peaks. Come back here, 5 peaks. So it is, this one's wrong, this one's wrong, this one's wrong. You know, straight away, there are 6 of them, we knocked out 50%. All right, so we're down to the last 3. And if we look over here, let's just look at each spectrum. So the mass to ion ratio is 1:6, so it's technically over here, but we can't see it. Okay, now too weak to be observed. So what are we looking for here? So while I was doing that, I noticed there were some molecules with CLs, but then we eliminated it. So as you can see on the mass spectrum right here, there's no 3-to-1 peak. So remember, 3-to-1, it has to be 1 over here, and then let's say if this is 60, for example, if this is 62, it has to be 2 units apart. So this is not a CL, this is not a CL. Don't get trigger happy and just, you know, assume that it is a CL. It's going to be very, very obvious. Okay, so from the mass to ion, from the mass spectrum, we can see the molar mass, the molecular ion is 116, which tells us the molar mass is 116 grams per mole, which tells us there's probably no nitrogen or even numbers of nitrogen, most likely no nitrogen. And there's no CL 3-to-1 peaks or BR 1-to-1 peaks, okay? And if you look at the IR, oh my god, this IR is so boring. This is CH, and that's it, nothing else. So there's no OH, NH, no C double bond O. Actually, that should be, is that 15? At peak, because this is telling me there's a C double O bond. Wait, did I get the wrong spectrum? Let me see. This is 70, so this is most likely a CO single bond. Yeah, there must be a, I think I must have grabbed the wrong IR, because there should be a peak here. Because if there's a C double bond O from the max, because I was copying and pasting spectrum, so there might be something here. I don't know. Let's actually look at this. I'm trying to figure out the answers, as you can see. Yeah, so I may have grabbed the wrong one, but there should be no OH nor NH, but there should be a C double bond O, because I can see that here, because it's 170. You shouldn't get two contradicting spectrum like this, because I may have made a mistake, or this is too low. Should be, this is 1500, that's too low. Should be 1650 to 1800, so there should be another peak here. Maybe I just grabbed the wrong one, doesn't matter. All right, so this is C double bond O for sure. There are 5 peaks. And this one is 70. If you go back to the table, you're going to see 70 parts per million is most likely a C single bond O. So bear that in mind. Let's come back. So straight away, this one's gone because this has a double bond. We don't have double bond. And then this is a ketone, and this is an ester. So straight away from that, this C single bond O, this right here, it should be this one. This one should be wrong. Okay. And if you want, you can actually grab a calculator and calculate the molar mass, because the reason being is actually pretty obvious that this 5th one is wrong, because if you actually look at how many carbons there are 5 carbons, there are 10 hydrogens and 1 oxygen, and this is 60, 70, 10. This is 16. No way on earth this adds up to 116. So that's got to be wrong. So that's one way you can quickly. I mean, look at how many carbons there are. There are 6 carbons, 2 oxygens, 116 grams per mole. That seems about right. Okay. Now, how do we determine? How do we write about this? So again, I just want to show you the whole thing. I just want to show you the fragmentation part, because like I said, I've done quite a bit in my other videos, so you can check those out for more thorough explanation, but I didn't do the fragmentation, so I just want to do it here. So the easiest way that you could do is to just bear in mind this weighs 116. Okay, so you can start cutting. What you could do is to look for the base peak, which is 41, 42, 43, 43. So what's 43? So this is 15. Found it right here. Cut it this way. This is 15. This is 15. This is 13, and that's 43 right there. So this is 43. So my fragments on 43 is CH3 CH plus. This is 43, and then what's 116 minus 43, and that's going to be 73 grams per mole, and then boom, right there, 73. So this is going to be my CH2C double bond O CH3 fragments. Okay, so you just say this is a correct one because it has 5 carbon environments, it has a C double bond O, which is confirmed on the IR NMR, you know, tell us where they are, and they have the CO peak, which is on the NMR. I have no N's, no blah blah blah, which is confirmed by here, which is confirmed by the IR. And then the fragmentation, if you look at the mass spectrum, there's a peak, there's a base peak at 43 MZ, boom, this is fragments. And then the other one is 73, boom, it's right here. So this must be a correct molecule. Okay, so you just need to thoroughly explain it. Okay, now just on the last bit, I want to do it really quick. Now I do this every single year, and then, you know, you'll be surprised. I emphasize this so many times every bloody year, and then you'll be surprised how many people still get it wrong. You know, it's just incredibly frustrating. Like, let's say, let's just draw you a few scenarios, okay? Let's just draw you a few scenarios. I do this every year, and then people still somehow get it wrong. It's just, it can be incredibly frustrating, but, you know. All right, so let's assume these are the furthest right-hand side peak. Okay, so they're nothing else on the right hand side, and these would help us tell us the molecular line. If this is 55, 56, if this is 55, 58, if this is 55, 56, I don't know why 55, 56, why not? If this is, oh, probably not 55, like I said, this is 1110, and this is 112, this is 1110, this is 116, this is, again, don't quote me on these numbers, like 120, 122. I say, for example, if we were to use these to determine the molecular line, you know, you can probably pause the video and just, you know, tell me which one's the molecular line for each of these situations, because if you get this wrong, that means you're most likely gonna, because if you get the molar mass, if you get the molecular line wrong, that means you get the molar mass wrong, that means you get the nitrogen number wrong, that means you get the IR wrong, that means your whole thing's wrong. Okay, so this is absolutely essential. So you do need to make sure that you can do this. Okay, so hopefully this is enough thinking time. So here we go. So the first one, this is clearly really short, 1 unit to the right. So look to the furthest right hand side, we see a really tall peak, and we see a really short peak, 1 unit to the right. So this is our M plus peak, and this one is our M plus plus 1. So the molar mass is going to be 55. Okay, so the molar mass is 55 grams per mole, which means we have at least 1 nitrogen. All right, now this one here, this was 55, this is 58. So we obviously go with the furthest right hand side, and they're equally tall, so we go to 58. Okay, now what if we have one here? This is 55, this is 56. Don't think this is a carbon. If this is a carbon, it will be on the right hand side, like the one that we have up here. So this is the molecular line peak. Now if this is 110, this is 112, so this is 2 units apart. This is a 3-to-1 relationship. This is M plus, this is M plus plus 2, showing us that there's chlorine. So this is your M plus peak, which is 110. If this is 110, this is 116, so this is our molecular ion peak, even though it's really small, but it's 6 units apart, so it cannot be a carbon isotope. If this is 120, this is 122, so that means this is an M plus peak because it have a 1-to-1 ratio, 2 units apart. That means you have a bromine. Let's just do one more really quick, actually 2 more. If I have one here, 1 tall one, 1 tall one, if this is 55, if this is 56, you cannot say this is the 56 is a carbon isotope. That's way too big. So we go with the furthest right hand side. This is M plus peak. Okay. Now since we did this one up here, if I have one here, if this is 60, this is 62, you're not going to tell me that this is bromine. All right, because remember, bromine weighs 79. How can something weigh 79 have a peak at 60? That tells me it's bromine. That cannot be right. So you need to understand that it's not bromine. So this is my M plus peak, because we go to the furthest right hand side, because the Br weighs 79 and 81, so it cannot be that one. Okay, so hopefully this has been helpful. It's quite a long one, but it's for 3 credits internal, and I don't have to make another one. I think this will be good enough for the future years until the standards are changed. Okay, so hopefully this has been helpful. Leave a like if you found this helpful. Share it to your friends or any other one that you know that are struggling in chem. And I will start recording some examination videos because the exam seasons are almost up. So yeah, all the best with your studies, and I will see you guys next time. Bye bye.